talk about Schur functions, specifically generalization called Skew Schur functions. Now, recall the definition of just the Schur functions in terms of Tableau. So here's how we are going to define, here's how we defined the Schur function as lambda x in the case of infinitely many variables. This is just x to the type of t varying over all the semi-standard Young tableau of a given shape lambda. Right? So, example, of course, if lambda were this, then what it means is you have to try and fill this up with all numbers 1, 2, 3, all the way to infinity. And what are the ways of doing this? Well, you can put a number I here. You can put the same number I there if you wish. But the number j that you put below has to be strictly bigger than I. Okay, or else, so this is I less than j. So that's case 1. Case 2, you put I here, and then you put j here, and well, you put the same number j here. Okay, I less than j. Or you can just have 3 numbers I, j, and k. In which case, well, all you have is this I is less than j, I is less than k. Okay, now, so what are all the possible Tableau? I guess we have written all of them down. Now, the definition of the Skew Schur function for this shape, which is the shape 2, 1 of the Schur function, is the following. It's all Tableau, the first kind will give me type xi square xj. All Tableau, the second type will give me xi xj square. Okay, and now Tableau, the third type. So observe, I could either have, j less than k or k less than j. So this is like saying I just want all possible xi, xj, xk. So here I've assumed that j is not equal to k. Right? Now, but the point is that the same monomial can appear in 2 different Tableau. So I need to have a 2 there for all I less than j less than k. Okay, why? Because I can have I, j, k, for example, 1, 2, 3 are the 3 numbers. They will occur like this as either as 1, 2, 3 or as 1, 3, 2. So I have 2 Tableau which will both give me weight x1, x2, x3. So this is the total sum. This in terms of the monomial symmetric function is, of course, as you can see, this is m21 plus 2 times m111. Okay, so that's the Schur function in terms of Tableau, the infinite version. Okay, and we had seen earlier when we talked about the Schur function in n variables that this coincides with the usual definition when you set xn plus 1 onwards to be 0. Okay. So now what we are going to do is to define something called the Skew Schur function. It has almost the same definition, except the shape that you fill things into is of a slightly different form. So here's, say, an example of a shape. So here I have some shape lambda, but what I do is this, I have also sort of an inner shape. So for example, here's a shape mu. There's an outer shape and an inner shape. Okay, so what I don't allow is to fill anything in the inner shape. So maybe I can even say this is my inner shape. So here's my mu. So we have an outer shape which is lambda and an inner shape which is mu. And the boxes that survive are, that shape is called, it's not quite the shape of a partition. It's lambda mod mu are just these ones. So there are just 4 boxes in this example which are part of lambda but not part of mu. And what we demand is that we should fill those up with the numbers 1, 2, 3, etc. in such a way that it satisfies the properties of semi-standardness. Okay, which means weakly increasing along rows and strictly increasing along columns. So here's an example. I could put, I can put 2 there. I can put the number 1 here. I can put, well, I have to put a number bigger than 1 here. Say 2 again. So here's this is a very simple example, but I just wrote out one of these. So the Skew Schur function S lambda mod mu of x is by definition, just take all semi-standard Tableau, whose shape is the skew shape, as it's called, lambda minus mu or lambda mod mu. Okay, so that's the definition of the Skew Schur function, and seems like a strange thing. Why would you want to consider this? Schur functions seem good enough, but these actually appear naturally. They already made an appearance when we talked about the Peary rule. Okay, so let me recall for you what the Peary rule said. It was a rule for multiplying a Schur function with a homogeneous symmetric function. So it said if I had to a complete homogeneous symmetric function, if I wanted to multiply the Schur function S mu with the symmetric function hk, then it said that the answer is of the following form. It's all lambdas. It's a sum over S lambda. And what is lambda now? So let me just use this mu notation here to say lambda is obtained from mu by attaching a horizontal strip of size k. Okay, and recall what horizontal strip meant. It just meant that if lambda is, say, this partition here, mu, if mu is this partition here, and I need to attach k boxes to the shape of mu such that no two of those boxes are in the same column. So I can attach what we call the horizontal shadow. So I can attach boxes like this, but no two, they can't be one below the other in the same column. So, and total number of blue boxes that I have attached should be k. Okay, so all such diagrams that I can generate from the diagram of mu by attaching k boxes, no two of which are in the same column, that set is what I am calling mu tensor k, the set of all such diagrams. Okay, now the point is we actually could iterate this as follows. So we did iterate this to write the h's in terms of the s's, but we can also iterate this with some starting point S mu on the left. Okay, so what is the next step? So I suppose I had k1 here. Okay, so it's like I must take the original shape mu and attach k1 boxes such that they form a horizontal strip. Okay, now suppose I iterate this like we did in the usual Peary rule, and I also multiplied this by hk2 here. Okay, so which means I'm going to now multiply another complete symmetric function hk2, and then I ask what will I get? Well, I just multiply hk2 on the right, and now I'm going to be able to use the same thing again. So let me call this now S gamma. Okay, the new guys are the gammas. And what are gammas? Well, gammas are all things obtained by attaching k2 boxes to lambda, where lambda ranges over all partitions obtained by attaching k1 boxes to mu, right? Such that these k1 form a horizontal strip, similarly k2 form a horizontal strip, right? So again, now it's starting to look exactly like the Peary rule, etc. Okay, and now if you go back and see, how the Peary rule finally worked out. So there we would not have chosen there's no S mu. We would have taken mu to be the empty partition in that case. But now if you start with some S mu, then what this finally says is that if you take S mu and you multiply it with, say, hk1, hk2 and so on. Okay, so maybe I'll call this h mu, where mu is the partition k1, k2, etc. Okay, so h nu is just hk1, hk2 and so on. So this by definition is just nothing but you start with, well, the answer is all lambdas. And what is lambda? Lambda is obtained from the original mu by first attaching k1 boxes, then to that answer attaching k2 boxes, etc. You attach kl boxes such that at every step they form a horizontal strip. Okay, and this, if you remember, is exactly this sort of tower is what led to the definition of semi-standard Young tableau in the first place. Okay, and the way we would do it is to put ones in the first set of boxes. You put a 1 there. This one is not too visible. Let's use another color. So 1 in these boxes, the blue boxes that you add. Then you put a 2 in the yellow boxes, and then the next step, whatever you add, you put a 3, and so on. Right? So that's sort of how we reinterpreted this tower, the sequence of shapes that you form, as being a semi-standard tableau. So this can therefore be written as a sum over all possible lambdas of, with what coefficient does an S lambda appear? Well, with as many semi-standard tableau as there are, but now the shape that's formed is the mu is sort of taken out. You are not allowed to fill the mu. The outer shape minus the mu. Okay, that times S lambda, where this is nothing but the number of semi-standard Young tableau of shape lambda minus mu, or equivalently the number of towers that you get by this process. Okay, so therefore what this implies is that this is exactly so k lambda by mu S lambda. So what does this mean? So we call our definition of the Skew Schur function. It's just x power t or type t ranging over semi-standard Young tableau of shape lambda minus mu. Equivalently, this is just summation k. It's the number of semi-standard Young tableau of shape lambda minus mu. Oh, sorry, I made a mistake here. So I should have said. So there is a new. Okay, sorry, this should have been a new to start with. So let's get this right. So this is not a lambda anymore. Sorry, that was a lambda. Yes. So that was a lambda. So that's a final shape, but I forgot to put the new here. So the number of 1s, 2s, 3s that you fill into the semi-standard tableau are you add k1 boxes in the first step, k2 in the second step, and so on. So the new should have also made an appearance somewhere. So there's a number of semi-standard tableau of so I should put a new here. It's Koska number k lambda minus mu comma new of type new. Okay, good. So now we are in good shape. So this is k lambda minus mu, and then when I say that the type of that tableau is new, I just mean it's the monomial expansion. So this is what I know. Okay, so now that was my definition of the Skew Schur function. Okay, good. So now we are in good shape to put all this together. So what are we saying? So observe, therefore, now comes the interesting part. We are saying the Peary rule is the following. It says, how do I multiply S mu with H nu, and how do I expand it into Schur functions? Okay, now I'm going to use the inner product that I defined earlier. Recall that the Schur functions are an orthonormal basis for this inner product. So I'll rewrite this in terms of inner products. This says that this is nothing but k lambda minus mu comma nu, right? Because that's just the coefficient of S lambda in the answer. Okay, good. Now on the other hand, what does this thing here tell me? It says that the monomial expansion of the Skew Schur function has the same coefficients. Okay, so this is just the expansion. So I take the expansion of S lambda minus mu, but from that expansion I want the monomial expansion. I want to pull out the coefficient of m nu. But the inner product had the following interesting property, that the m's and the h's formed a dual basis. Okay, so to pick out the coefficient of m nu, I must take the inner product with h nu, and that again is the same number just by definition. So what does it mean? It says that these two things are actually equal to each other. So this is an interesting identity. This sort of tells you what Skew Schur functions really are. you should think of them as being the functions which satisfy this identity, that the Skew Schur function is that unique function whose inner product with all the h's is given in the following manner. Just take S mu H nu with S lambda. Okay. Now, so what is this? This is sometimes described by saying that you look at the operation, which is multiplication by S mu, and so the operation of skewing, looking at the Skew Schur function is kind of the adjoint of that operation. Okay, so we'll make it clear in just a moment. So what does this mean? Corollary, I can now, since H nu's form a basis, any symmetric function can be expanded in terms of the H nu, right? And this inner product is linear, so I conclude the following, that I take S lambda minus mu with any symmetric function f, not just the H nu. Then the answer is, so observe the H nu appears here, right? So this is just S mu f, comma S lambda, and this property is now true for all symmetric functions. Okay, just by linearity. Okay, good. So what does that tell me? In particular, it says that if I want to compute, therefore, I will replace f by Schur function, then this is just S mu, S nu, comma, S lambda. Okay. So if you wanted to expand the Skew Schur function, S lambda minus mu, in terms of Schur functions, right, the coefficients are exactly going to be these inner products. It turns out that those inner products are nothing but the coefficients which appear when you do the following operation. You multiply these two Schur functions together. You multiply S mu with S nu, and that product you expand again in terms of Schur functions. Okay, and you find the coefficient of S lambda in it. Okay, so this taking a product of Schur functions and expanding them again. So this is a very important problem. Question of how to decompose a product of Schur functions. Okay, so this guy has a name. This coefficient is denoted C mu nu lambda. Okay, and of course it's well, what do we know about it? I suppose nothing much at this point, but let me just give this a name. This is called the Littlewood-Richardson coefficient. So it tells you how to multiply two Schur functions together, if you wish, and then expand the answer back in terms of Schur functions. Okay, so let me tell you without proof this a combinatorial rule for computing the Littlewood-Richardson coefficient. So here's the rule. It's called the Littlewood-Richardson rule, the LR rule. Says that if you were trying to find C mu nu lambda, the Littlewood-Richardson coefficient, here's what you could do. It is the number of semi-standard Young tableau. Okay, of skew shape. So this is now of shape lambda minus mu. Okay, and type mu. So observe, so far this is more or less the number that we already looked at, right? So you look at things which are of type lambda minus mu, of shape lambda minus mu and type mu. This number tells you how to expand the Skew Schur function in terms of the monomial, in terms of the complete symmetric functions. But what we are interested in is how to expand the Skew Schur function in terms of the Schur functions. Okay, so we are trying to do the same expansion of the same object, but with respect to a different basis, with respect to the Schur basis. But it's interesting that the rule to a first approximation has the same objects. Okay, it's a number of semi-standard tableau of shape lambda minus mu and type mu, satisfying an additional condition. Satisfying okay. Now what is this additional condition? It says that so what is a semi-standard tableau? So let me just demonstrate it by example. So suppose I have so let's say this is our tableau, and I mean this is our lambda, the outer shape, and I've got an inner shape mu, which maybe I will just assume is just this much. That's my mu. Now what I want is to take this outer shape lambda minus the inner shape mu and try to fill it up with numbers of type nu. That is, I should take nu1 1s, nu2 2s, and so on. So I start filling it with 1s, 2s, 3s, satisfying the semi-standardness condition. So which is I can put 1s and 2s, etc. various places such that they are weakly increasing. So maybe I'll put 3, 4, 5. So here's a way of filling it. Okay, now associated to this, so this is a semi-standard filling for sure. Okay, now associated to this, I will have what's called a reading word. Okay, I associate something called a reading word. Okay, sometimes called the reverse row reading word. So which is the following. I just read these numbers 1, 2, 3, etc. as follows. I start from top and I read right to left this way. Okay, so in this case when I read, I get 1, 1, then the next row is 3, 3, 2, 2, 5, 4. Okay, that's my reading word in this case. Now the requirement, this additional condition is the following, that this reverse row reading word that you have must be what's called a ballot sequence or a lattice permutation. Okay, satisfying an additional condition. So let me say condition star. What is this new condition star? The condition star says that the reverse row reading word must be a ballot sequence. Okay, now what that means is when you cut this word in at any point, okay, you truncate this word anywhere and just look at the initial portion of the word, then there should be more 1s than 2s in this word. There should be more 2s than 3s, more 3s than 4s, and so on. So for all I, there should be more i's than I plus 1s. So ballot sequence means every left subword contains more i's than I plus 1s. Okay, so that's what a ballot sequence is. So now here in this example, this is not a ballot sequence because, well, if you sort of truncate this word here, then you'll notice that it's got a 3 but it doesn't have a 2. Right? So there are more 3's than 2's if you truncate it at that point. Okay, so that's not going to be a ballot sequence in this case. Okay, so what the LR rule says is that you need to have you always need to have more 1s than 2s than 3s than 4s and so on, no matter where you truncate this reverse row reading word. Okay, so let us see what would be an example of something in this case, which is in fact a ballot sequence. So what we could do is maybe, okay, let's try and just redraw this quickly. So I have 4 and 4, then 2 here. And these are the two things that are part of mu where I'm not filling anything. Okay, so I have to fill ones in the first row. That must be a 2. So it's going to be 1, 2. And that one's got to be a 3. So it's 3. So in this case, there's really only one way of filling it, such that it's a ballot sequence. So you can check that I can't really do anything else here. Okay, because I always need to see more 1s than 2s than 3s and 4s and so on. Okay, so let's see if we can find a slightly different shape where it's possible. To find something slightly different. So for instance, this guy here will contain 1, 1. So here's an example of, so I mean, I just took a very simple shape, lambda the outer one and mu is this inner shape. So the thing with both ones is a ballot sequence, because when I read it, I just get 1, 1. Or if I put 1, 2, then that's also a ballot sequence. Okay, but observe 1, 3 would not be a ballot sequence, because I would see more 3s but no 2s. Okay, so anyway, so this is the LR rule. So as I said, if you did not have condition star, then this number that you are trying to count is exactly that number k lambda minus mu comma nu. Okay, which is going to tell you how to expand the Skew Schur function in the basis of the h's. But since we now want to expand it in the basis of the Schur functions, the SS, the that number is actually smaller. What you get is an additional condition star that needs to be satisfied. Okay.